Thank you very much for coming to episode 1 of the Science Saturday. Not quite sure what season it is, but it's 30 at this point. There are some people that need no introduction. I'm not one of them, so I'm going to introduce myself. I'm Anders Carlsson, and I've been teaching here in the physics department actually by now more than half my life. And most of my research has been in the area of biophysics, but lately I've also developed an interest in renewable energy, and that's what I'm going to talk about today. One thing I want to ask you is make sure to ask questions if anything comes up during the talk. So just go ahead and interrupt. I'm sure a lot of people have the same question. So the background of this talk is that we want to reduce carbon emissions because they're causing global warming, which is a disaster in progress. And a substantial part of our CO2 emissions are due to electrical generation. So I'm going to talk about how we can make electrical generation more renewable. Lately, over the past decades, we've seen that carbon-free sources have rapidly expanded. But the thing about solar and wind is that they're not always there when you need them. So their intermittency makes it hard to achieve 100% renewable energy. And so to deal with that, we need to be able to store energy or use some amount of fossil fuels. And so today I'm going to ask 2 questions. First of all, what would a 100% renewable energy system look like for the St. Louis region? Second of all, should we go with, should we really be 100% renewable, or should we maybe be 98 or 99% renewable?
Do we want to try for hamburgers tomorrow afternoon?
I'm open to that.
Breakfast at church and hamburgers at your house. Earth's temperature is rapidly rising.
Please mute yourself.
That's Walter.
I don't think we're mute.
And so this is the problem, that this is a plot of temperatures over the past 1,000.
How can we mute ourselves?
We are muted. They mute us.
They said, please mute yourself.
You're not muted.
The host might have everyone.
The hamburger lady is not muted.
She said, hey,
I have to find a way to mute all the participants. If there's any experts out there unmuted.
What were the options under the mute again?
Speaker.
Can you click on that?
I
Could
do.
you not give me the mute all option?
Meeting when it starts.
You could message all the
There's a button on the bottom left corner of the screen with a microphone. If you press on it, it will mute you.
Well, I don't want to mute myself.
No, they're telling.
Oh, okay, yes, thank you. All right, well, thank you very much. I think that solved it. And so we've seen, if we look over the past 1,000 years, we have a pretty slow drop in temperature. Then roughly since the Industrial Revolution, the world average temperature has been climbing precipitously. And it's pretty clear that this is due to the CO2 that humans have put into the atmosphere. And this has impacts all over the place. As you know, especially in St. Louis, we have frequent and intense storms, and you can't attribute any given storm to global warming. But nevertheless, there are people that specialize in attributing statistics of storms to global warming, and they argue that we are seeing more frequent and intense storms because of global warming. Rising sea levels, that's very rough for coastal cities, and of course there are entire island nations that will disappear. Melting glaciers is a very bad thing. Warming oceans are bad from the point of view of the fish that experience a different chemical environment and cannot survive in the new temperatures. It also wreaks havoc on people's livelihoods. Farming becomes difficult, completely changes character, and also it does harm to animals. And so about a quarter or more of the CO2 emissions are due to electricity generation. Okay. So here are some pieces of a possible solution. So I drove out to Kansas City about a week ago and was pleased to see a number of solar arrays along I-70 on the way to Kansas City. And these are, this is feeding into Ameren's energy supply, which is a good thing. And if you drive up to Chicago, you actually tend to see more windmills. So as you look around you, you drive anywhere, you see that this is taking off rapidly. Okay, so that's, those are our basic sources. And so now, what is it that we have to provide? Well, this is the electrical load in a region of the Midwest, which I haven't taken as a proxy for St. Louis. And it's one is just the average. So that left axis doesn't have the absolute mean. And you can see the demand maximum is July and August. And that's not surprising. That's the big air conditioning season. If people have start to use heat pumps more for heat, that may shift, and the winter may become a larger time of load. The average power is about 4,500 watts. Now, I want to mention here, this is not just the power that's being used in your household. This is the total electrical power being used in the region. And I'm dividing that up by households. So what is 4,500 watts? Well, a space heater draws about 1,000 watts, a small space heater. So it's basically like we're running 4 small space heaters all the time. And the other thing to notice about the demand is that the variations are not huge. It's maybe 30–40% variations, but it's pretty much around the average. So this is what our system needs to provide. It needs to provide a pretty constant supply of electricity. Now, let's look at our sources. So solar energy. I've thought it out 1 year, and there are some great data sets that are available, and I got a hold of a data set that traces wind and sun from 1980 to 2020 for those 40 years every hour. And so this is a piece of that larger data set, and it goes from the middle of 2018 to the middle of 2019. And you can see that there's a dip right around January 1st. And of course, we know that that's when we have the least sunlight. That's when the earth is turned away from the sun. And you also, of course, it's not a smooth curve. You see, it's a very rough curve. And that's because sometimes we have cloudy days and sometimes we have sunny days. System. And so on the bottom, I've blown up a piece of that. I've taken just 20 days and I plotted out the energy hour by hour in those days. And what you can see is that for every day, there's a peak. It goes up to about 500 watts per square meter. And let's compare that to the top plot. In the top plot, we're getting 1,000 watts per square meter, kind of at the very middle of the summer. And so, does that make sense? So what's a square meter? Well, that's a square meter. And 1,000 watts is a space heater. So, if you imagine the solar energy on a hot summer day coming through a square meter, and that would seem to be about the same as you get from a space heater. So that's what that number means up there. It's 1,000 watts per square meter. And now these 20 days are in the winter, and you can see that the whole scale is much lower. And you see that there are some really bad days, like you look around day 6 there. It's like 10 times less intensity than we were getting in the middle of summer. Yeah.
That's overall wavelengths, integrated
Yes,
overall.
that's correct. Yeah, that's all wavelengths. Yep. So that means on that day 6, you're going to have some other way of getting your energy. But so what you see is that there are, of course, every day, there is a peak and a trough from day and night. But then we also have these random day-to-day fluctuations. And this is one more thing that makes it challenging to design an energy system that supplies a constant output of power to meet our needs. Okay, let's look at wind then. So this is same kind of plot for wind. Now, this mysterious phrase, wind power factor, up on the left, and that refers to the fact that a windmill has a maximum energy output. Let's say you imagine one of these big windmills along I-55 going up to Chicago. They're maybe 100 meters above the ground, when there's very little wind, they actually don't do much at all. It climbs for a while, but then it reaches a peak. And then after that, actually, it has to be turned off because the wind gets to be too strong. So there's a maximum energy that a given windmill can output. And that's what this is referring to here. It's saying, what day, how many days are you going to have the maximum output and how many days are you going to have much smaller output? And so this is not quite as systematic as what we had for the radiation from the sun. You can see the maximum, it turns out, is actually around March, April. Maybe like today. Today's a windy day. And the trough tends to be around July and August. So that's kind of a good thing, because it means that the sun has its maximum power in July and August, and the wind has its minimum power. So to some degree, these two sources can compensate for each other's weaknesses. But the thing about wind is, if you look at the bottom, that it varies even more extremely than the solar does, because these are just random fluctuations and they go down to 0. So those are kind of the relative strengths of these two different sources of energy that we're going to put into our system. Okay, so this is the kind of system we're going to look at. We're going to have solar panels, we're going to have windmills, and then we're going to have some kind of storage. And right now, in the calculations I'm talking about, I've been looking at lithium-ion batteries, which is what we have in cars, but there's other possibilities coming along in the future. But one thing I want to get across is that if you want reliability, you can either build much more capacity to cover even those partly cloudy days, or you can have storage, one or the other. And the choice between those is going to be determined by the relative cost of storing electrical energy versus generating it. Okay, now, so I'm going to be telling you about some designs that I've been making. Let's see if I can move that. No.
You can minimize the pictures on the right.
Yes, let's see.
There's a little X there if you want to show the title at the top of the. Yeah, right there.
There.
Oh, exit out. Yeah.
Hard to get, might work better on this one.
There we go.
Yeah, thank you. Okay, so I'm going to be telling you about the design of some of my designs for renewable energy systems. And I don't want to say that I'm the first person that's done this. In fact, this has become a cottage industry. So this is the number of papers per year that have gone into studying various kinds of highly renewable energy systems. So this is really a field of study that's taking off. One thing is that they don't agree with each other. You read different papers that should be looking at the same system, but they end up getting rather different answers. So we're going to do this by designing the system, choosing the system that supplies our energy needs and has the lowest cost. So we need to talk about cost a little bit. And so for solar panels, the way, if you buy one, the cost will be given as something like $1,500 per kilowatt of capacity. And what does that mean? If a solar panel has a kilowatt of capacity, that means on the best possible day, it'll generate a kilowatt or 1,000 watts of energy. So that's just a way of saying what that means. It's like a nameplate number. It doesn't mean it usually generates a kilowatt. So it's just on the best possible day. Okay, and as I mentioned, a kilowatt is the power that's drawn by a space heater. On the other hand, storage costs about $200 per kilowatt hour. Okay, now why are we talking about kilowatt hours? Well, the reason is that if you run your space heater all day, it's different from running it just 1 hour. In other words, the amount of energy that you use, it's determined by the power of the device, but also how long you use the device. And so it actually is measured in terms of the power times time. And so a kilowatt hour is what it takes to run the space heater for an hour. And that costs about 10 cents. But now storing that energy costs about $200. So the cost of storing the energy is 2,000 times the cost of buying it in the first place. So here's an analog of this. I've got a bottle of iced tea here. This iced tea is worth maybe $1. Okay? And if this bottle were to cost 2,000 times more, this would be a $2,000 bottle. Okay? And at that point, I'm not going to call it a bottle. I'm going to call it a $2,000 fluid storage device. Wow. Okay? I'm willing to part with this one for only $1,500 at the end of the lecture if anybody's interested. But what I want to get across is that our current modes of energy storage are expensive.
Can you Go a little deeper into what the $1,500 cost represents. Is that like retail price or
No.
is that accumulated manufacturing cost?
Thank you. Well, this is actually if somebody, if a utility installs the solar panels with all the wires and everything, so it's kind of ready to go and start generating electricity. That's what that 1,500 will be for. My experience as a homeowner, having gotten solar panels installed on my own roof, is that it's significantly more for a homeowner. Yeah.
What does Tom Sauk Reservoir cost?
Well, it's a very good question, but you're talking about hydro storage. Well, I mean,
18th,
where
19th
you can
century
do it,
cities.
that kind of storage is probably around 10 times cheaper than this. It's probably about $20 per kilowatt hour. But the trouble with pumped hydro is you've got to have a place for it. You know, it's only certain places that are suitable for that. And some of them are, and where, in fact, as far as grid scale storage, that's probably the largest amount of storage that's in use right now. There's not a lot of batteries on the grid, although they're starting to take off. Thanks. Okay, so yeah, those are the numbers per unit, but really what matters is how much is this going to cost to us in terms of our everyday life. So let's think about the cost in a different way. And I'm going to talk about a baseline solar generation capacity. And what I mean by that is that we have enough panels so that over the course of the year, they generate the same amount of electricity that we use during the year. Now, if we do that, that means they're generating too much in the summer and too little in the winter. But that's just a useful reference point to think about the generation capacity. And so that would be, turns out, if you work it out, that would cost about $35,000 per household. And it would take up about 50 square miles. Now, anybody happen to know the area of the city of St. Louis?
61, I think.
Yeah, I think that's right. Yeah. So I'm not talking about just the city of St. Louis here. I've been looking at a region that's about 200 by 200 miles square around St. Louis. So out of that, it wouldn't be hard to come up with 50 square miles for solar panels. And on the other hand, a battery unit to handle a day's energy consumption costs about $22,000. All right, so now I'm going to design a sequence of progressively less boneheaded energy systems. So one way to design a totally renewable energy system would be to have so much capacity that even on that really bad day 6 that we looked at before, even then you have enough panels to cover that. That means you need actually about 7 times the baseline capacity. And then you need half a day of storage to get through the night also. So you work that out, that cost would come out to about $260,000 per household, okay, which not everybody has lying around. If you do, I'll be happy to talk to you afterwards about some property I have on the coast of Florida. But this is just out of the question. This is way too expensive. So what can we do? Okay, so we can optimize the amount of solar and the amount of storage. And this is what our calculations do. So we wrote a computer program that it follows the amount of energy in storage over time. And let's say we start off with a full battery. We've had a lot of sunlight. And then the computer program, it's just like every hour, it ticks forward. And as long as we're getting enough sunlight, then the battery stays full. But if we get a dark day, then that battery starts to empty. And we follow that process of the battery emptying, and hopefully it doesn't get completely empty. If the battery gets completely empty, then the system has failed. So the requirement is not actually to be 100% renewable. It's 99.97% renewable. So that's what we look at in these designs. So we look at all these combinations of a certain amount of storage and a certain amount of generation capacity, and see the ones that are 99.97% there, and we choose the least expensive one. And that's the system on the top there looks like that. It's got about 2 days of storage, and it's got between 2 and 3 times the baseline capacity of solar. Okay. And that brings the cost down to $150,000 per household. Okay, that's still really a bundle. So in the next step, we can add wind to the mix. And then you see that wind actually becomes a larger component than solar. You see that we also have less storage, and we don't need as much storage now with the wind, because the wind and solar are kind of complementary. So they make, to some extent, they make up for each other's flaws. So now with solar and wind and storage, the cost is gradually getting down, and it's coming down to $85,000 per household. So one thing about these systems is that they actually, a lot of the energy goes unused. And in this case, it's over 50%. Of all the wind and solar energy that's generated, we just don't have any use for it. Although I'll talk a little bit later about how we might find uses for it. But that's kind of the price of reliability. The term is curtailment. That they seem to be inevitably connected. Okay, so now here's the question. Do we need to get all the electricity from renewable sources, or only maybe 97 or 98%? You know, what's a better choice? In other words, forgetting that last percent, are we using a pound of prevention to get an ounce of cure? And so that's, I want to show you some calculations we did for that. And so we're going to try to design what I call a socially optimal system. Okay, and by socially optimal, I mean that on the one hand, we're including the actual cost of building the system. But also for all the systems we look at, we're going to look at the costs of generating the CO2 from those systems. So there's going to be a penalty for generating CO2. Why not? That's our typical way of kind of limiting certain behaviors, is to penalize them. And to do that, we need to define the cost of the damage done by carbon dioxide emissions. And this is known as the social cost of carbon. And it's a number that's so many dollars per ton. And it's a way to try to define the value of the future damages done by a ton of carbon dioxide emissions. So let's make a quick estimate of that. First of all, I'm going to figure out how much worse is our life because of the CO2 that's in the atmosphere right now. Right now, it turns out there are about 1 trillion tons of CO2 in the atmosphere that we have put there that shouldn't be there. And so the question is, how much worse is our life? Let's do it in terms of percent. Like, is our life 5% worse, or is it 10% worse? Or what do you think? So how many people would say that the damage that they are feeling from global warming less than 5% of their overall quality of life? Okay, one vote there. And how about say between 5 and 15%? Okay, that seems to be the majority. And how about greater than 15%? Okay, got one there. So I'm going to then decide the average was 10%. Okay, so our life is 10% worse on account of global warming. But how do we turn that into a number? Well, one way to look at it, let's assume that this holds for everybody else in the world too. Certainly for some people, it's a lot worse, like if you live on a small island that's slowly disappearing. So the gross domestic product of the world, it probably has another name, but it's about $100 trillion. Okay. So if we are losing 10% of our quality of life, I'm going to say that that's 10% of 100 trillion, or that's going to be $10 trillion. So that's the value per year. And that's what's being caused by 1 trillion tons of CO2. So $10 trillion per year damages by 1 trillion tons. We can divide out the trillion. So we have it's $10 per ton every year. But now the question is, how long does that CO2 hang around? That damage isn't just being done this year. It's this year and every following year that the CO2 hangs around. And it turns out that for CO2 actually to go back into mineral form, where it's really not damaging anything, it takes about 200,000 years. Okay, so we're going to take our $10 per year and then multiply that by 200,000. And so that'll give us a cost of $2 million per ton. Okay, that's a big number. The economists don't like that. Economists have an approach to this that's called discounting. And it really means that damage that's done in the future is less significant than damage that's done now. Which has a lot of problems when you think about it. It means, for example, that something that's done to our grandchildren is less bad than something that's done to ourselves. But the logic is that we'd rather have, say, $10,000. We'd rather have it now than in 10 years, because we can always invest it and presumably come back with more than $10,000. So if we'd rather have a good thing now than later, that means a bad thing, we'd rather have that bad thing later than now. And that's true. You know, if you have some, I don't know, I guess I would rather have a toothache in a year than have it now. But the thinking is also that the people in the future will be wealthier than we are. Like think back to the late 19th century, living standards were very low. You know, do we think that those people in the 19th century had an obligation to sacrifice their standard of living so that we could live better? In that sense, you might, that's kind of an argument for discounting. And the argument is really that future generations are so much wealthier than we are, that why should we support them if they're going to be so well off? But again, when you go through the math of the models that they use, there's something called a discount rate. So that it's kind of like an interest rate. That's the way money would grow at 2% a year, but it's the inverse of that. It's that damage shrinks at this rate of 2% per year. Okay? And so 2% is kind of on the low side of what people use for that. And
hey, Mary.
Good morning.
Good morning.
Do you have company?
No, I do not.
Oh, okay.
can you mute, please?
Could the host The host or the co-host, please mute everyone.
Yeah, I'm just trying to find the mute all button here. Okay.
Or you have to go to each individual person and mute them, but you can do it from host controls.
It should be under participants.
Okay.
And you can go to the participant list and mute them there, but the rest of us can't do that.
There we
Except
go.
for ourselves.
Okay, thank you. Yeah. Right. Um,
Anders, I've muted everybody, so if you'll unmute yourself, then you can get back to talking.
Okay, are you hearing me?
Yes.
Okay, thanks. So if we imagine at 2%, and that's going to be over 500 years, that means that people 500 years from now are going to be living 20,000 times better than we are. And I can't even see what that means.
Isn't there an inflection point at some point too, where, you know, maybe we're saying that we feel like it's affecting us 10% right now, but you hit a point where it's going to be unlivable, and it's probably before 500 years from now.
I think so. Yeah. Yeah. So that's on the whole, I think this the fact is this discounting tends to give you a lot lower cost of carbon because you're only counting so many years, basically. And that's what the economists come up with. And I think it's numbers may be higher than what the economists think, but this is what the economists are thinking. So there's a range. So on the bottom there is the social cost of carbon. And there are different discount rates. And you can see that for the lowest discount rate, it maybe reaches out to about $800 per ton. And right now, the Biden administration uses a rate of $51 per ton. The Trump administration used, I think it was like $15 per ton. And so this is it's a very politically charged issue. On the whole, conservative politicians tend to estimate lower values of the social cost of carbon. And the highest number I've seen is one that was estimated in Germany that it would be about $800 per ton. So this is the range I've used, even though I think maybe the value should be even higher than that. So this is the system we're looking at now. We're going to look at solar panels and windmills, and also a storage facility, and what's called a gas peaker plant. So this is a plant that doesn't run most of the time. It turns out that the capital cost of a gas electric plant is pretty low, so you can build it and it's still okay not to use it most of the time. And so we put that into the system, and then we have an added cost. So the cost is the cost of the generation, plus the cost of the storage, plus the cost of the windmills, and now also plus the actual cost of generating electricity from the gas, as well as the social cost of generating the electricity. So that's the whole social cost of our system. And then we look at various systems, and we choose the system that has the minimum total social cost, the total, I guess, regular cost plus social cost. And this is what it looks like. So let me explain the plot here. So first of all, on the left, you see storage that's increasing as we go. toward the back of the plot, we have the increasing carbon cost that's on that lower right axis. And there you see that for a very low carbon cost, we have basically no storage, but as the carbon cost climbs, we get progressively more storage. And then we get more solar and wind, and then the deficit drops. And here I plotted 10 times the deficit, just so we can see it. So, I mean, the basic trend here is that as we make carbon more expensive, if we penalize that more, that then we get more of all of these things, the storage and the solar and the wind, and the energy deficits drop. Okay, so let's look at the deficits and the economics of this system. So again, it's social cost of carbon on the horizontal axis. And first look at the solid dots, and you read them on the left axis. That's the percent of our electricity that we have to supply from natural gas. And we're trying to get that to be zero. That's our goal. And now you're seeing that as the social cost of carbon climbs, that it comes down to like 6%, 5%, and then maybe 3% at the highest value of the social cost of carbon. And then to the right there, I have a couple of extra points. That's for a basically entirely renewable system where we have 0% from natural gas. And now follow the open circles. The open circles are the cost of the system. And that you read to the right. So it starts off at around 40,000 and then climbs up to about 60,000 as we get to $800 per ton. And beforehand, we had our completely renewable system that was like 85,000. So the thing to look at there is the difference between the 85,000 and the 60,000 that we're now getting for our socially optimal system. Okay? And so this is the price of those extra 3%, would be that roughly $25,000 per household, or maybe 30% of the cost of the whole system. Okay? And so this is the debate. I haven't really come down on one side or the other of this yet. But that's what we're talking about. Is that worth it? Spending those $25,000 to get the last 3% of renewable. Well, maybe we're not going to have to answer that question. Maybe things are going to get better in some way or other. Maybe storage will get a lot cheaper. And later on, I'll talk about some ways that might happen. So if storage gets cheaper, well, yeah. Then we use a lot less storage, and the system cost actually gets reduced by about 30%. So if you look now, this is the same kind of plot before, and look at the open circles here, and you're reading them to the right axis. You can see that the cost is not really climbing very rapidly as the social cost of carbon increases. And in fact, there isn't really that big a difference in the system cost between the completely renewable system and the one that's a few percent renewable. So that's one way that things might get better. Another way is that we could have a better transmission network. So the US transmission network is divided into various large grids. There's on the very left is something called the Eastern interconnection, the Western interconnection, and on the right, there's the Eastern interconnection. And those are the largest sub-pieces of the electrical grid, and they're carrying like huge amounts of electricity. But in fact, we don't have very good connections between those. So the amount of connections between these various grids is like less than 100th of the connections inside the grids. And that may change. It's something that at least has been stated as a priority of the administration to improve the electrical grid. And so why might that help? Well, here is, let's say, a similar kind of wind data that I showed before for St. Louis over a random 20-day period. So you see for the St. Louis region that there are huge variations in the data. And on the other hand, if you look at the US, now all the wind power in the whole US, the fluctuations are much smaller, okay? It's kind of in the same spirit as it's always 5 o'clock somewhere. It's in the same spirit, it's always windy somewhere. And so that means that if we happen to be having high winds up in Washington State now and there's nothing here, that then we could bring that electricity here. And this smooths out the fluctuations a lot. So this turns out makes a big difference also. And now the interesting thing is that the system ends up looking very different in this case. In fact, the system ends up being very much dominated by wind. The solar drops, and it's just because wind on the whole is a little bit cheaper than solar, and if you can get rid of the fluctuations, then that gives it a big plus. And then this also makes the system less expensive, and you don't really pay as much extra for those few percent. So these are all things that could be happening. You can combine them, and it gets even better if you say have cheaper batteries and you have better transmission. Then the whole system cost drops by about a factor of 1/2, down to about 30,000 per household. So let's speculate a bit. Let's think about the future, what might happen. The National Renewable Energy Laboratory has made predictions about how battery costs might drop over time. And this is for lithium batteries, which have seen vast improvements over the past decades. But now, when you look at these numbers, it's not really that dramatic. We're seeing maybe from 2030 to 2050, it's going to drop from 200 to 150, or just 25%. So that's not really earth-shattering. I mean, we were talking about factors of 10. So what else might happen? Well, there are many battery technologies under investigation. And one that I think is promising for grid storage is a so-called flow battery. And a flow battery is not a solid hunk like a lithium battery. It's actually 2 big vats of fluid. And these fluids are chemically different from each other. And so it turns out the battery runs by protons moving from one fluid to the other through a membrane that's between them. And so this is nice because if you want a bigger battery, then you just have a bigger vat of the same stuff. And what controls the amount of power, say how quickly you can get energy out of the battery, is a membrane between them, but you can also make that membrane bigger. So these are batteries that you can really adjust to the size that you want. And you can play with these chemicals, and so then there are materials problems for lithium batteries, getting lithium and cobalt, and those can potentially be a lot less for flow batteries.
My understanding is you won't get the energy density, anything like lithium ion, but so what at a utility, that's not important.
Yes, thank you for mentioning that. We couldn't put this in a car because in a car, we need batteries to be light and small. But for the utilities, that's not really an issue. And so this is promising. This is something that came out in Nature last year that was there are many chemistries that can be investigated for flow batteries, and this is one. And so you can read that. It says that it's going to be about $2.50 per kilowatt hour, whereas our lithium batteries are $200 per kilowatt hour. So that's a factor of 80 cheaper if it works. You know, there are of course many things that are promising, but don't quite work out. But since there are so many different promising things, I think they will. Okay, hydrogen generation and storage is another possibility. Right now it's not that efficient. The basic idea is that you take energy from solar panels, you use it to drive an electrolysis process that generates molecular hydrogen, and then the molecular hydrogen goes into a so-called fuel cell, which converts it into electricity. And the trouble is really that the fuel cells are not that efficient. And electrolysis has been going on so long, it's probably not going to get much more efficient than it is. And so between the two, the process is actually, I think, a little bit less than 50% efficient. But if we have these renewable energy systems, we have this curtailed energy. We have energy that we're just throwing away. If we're throwing it away, maybe it would make sense to make hydrogen out of it and have that as a piece of the economy. Yes.
Well, and hydrogen transmission would be actually way more efficient than electrical long distance transmission, right?
I think so. Yes. I mean,
The problem
you
with
put
that is
that.
I think hydrogen would require an upgraded infrastructure from our current methane pipeline system. I think hydrogen-
Yes, that's true. Hydrogen will escape more than methane will. Yeah. Okay, and now finally another possibility that interfaces with this thinking that we've been doing today is capturing carbon and storing it below ground. Recently, it's been shown that if you bring carbon dioxide and water down into basalt deposits, that the carbon dioxide actually becomes calcium carbonate. So it turns into a mineral. So it's possible to do that. So you could imagine that you could take gas from a power plant and send it down, and you could take the CO2 that's generated at the power plant, capture it before it goes into the atmosphere, and then you could send that down into the earth. Not for most of our generation, but for our few percent. And so then we could imagine this system, which with the carbon capture added on. And this would make sense if the cost of sequestering the carbon is less than the social cost of carbon. And my preferred cost of carbon is about $1,000 per ton. And so I think that there will be viable technologies for carbon sequestration that will cost significantly less than that. So that would put us in a picture where we have the solar and the wind and the storage, and then a few percent that's coming from gas-powered plants, and those gas-powered plants would be sending their CO2 below ground to be turned into calcium carbonate. Okay, I've said just about everything I want to say. I just want to mention one thing. Any pictures out there that there is a WashU outreach committee, which is happy to bring classroom experiences, demonstrations, or lectures like this one, for example, to schools. So just email that number if you're interested in having somebody come out. And that's about all I have to say. So, I mean, my feeling about this is basically optimistic. It's really possible to design highly renewable energy systems at a reasonable cost. And the question of whether they should be entirely renewable or mostly renewable, I think that's still open. And there are some key unknowns for planning future energy systems. And that's the storage cost and also the extent to which the grid is going to improve. And this is an issue because the systems that without, for example, extensive, without a good transmission network tend to have more solar. So if the transmission network improves over time, we could imagine that we could actually have overbuilt the solar, because with the better transmission network, then the wind becomes favored. So these uncertainties are something that we should be thinking about now and getting some idea of what the conditions are in the future. We should take that into account when we design our current energy systems. So I'll call it quits there, and I'm happy to take any questions. Yes.
Question. So it's been a long time since I read this article. Talking about Tesla.
Yes.
And Edison. And Tesla said he could have free energy for everybody in the world by harnessing light. Now, obviously, there would have to be a grid to capture. But if I remember that, in competing with Edison, he said we could develop systems to take lightning energy and to store that and then have free energy for everybody in the world. Have you heard of any theories that Tesla had about this?
I am not actually familiar with that theory, but I'm pretty dubious about it. And the reason really is the storage. Yeah, you would, I mean, our storage systems that we're designing, we find that the storage is like 1 or 2 days of load. But you'd have to have enormous amounts of storage if you're going to just grab lightning bolts and then store them.
You could put up kites like Franklin did. Let's channel it down to your lithium battery.
Yeah, but then also the thing is you can only charge batteries so fast. If any of you have an electric car, you are aware of that, the faster you charge it, the more you're going to degrade the battery. So that would also
ask another question. So during your lecture, you've been taking in oxygen and you've been giving out carbon dioxide. So, it's minuscule the amount you produce. But if you have 7 billion people on this planet and you get to 15 billion, are you producing a lot more carbon dioxide that goes into the atmosphere just because of
just by virtue of breathing?
Breathing. Right. If you're an astronaut and you have a certain amount of oxygen, and you use that up, you put carbon dioxide, you get carbon narcosis and so forth. Let's say, 100 years from now, if there are 15 billion people on this planet, you're going to be producing a lot more carbon dioxide because of breathing.
Let me try to answer that. I'm going to say, I think my body is on the average running at about 100 watts. That's about the amount of energy that I'm producing. And so, on the other hand, I'm using, I guess our energy consumption per capita, electrical energy is about 1,500 watts. So I would say maybe I would be like 7% of the whole then, which, is not, I mean, or I guess my breathing would be 7% of the whole consumption. So I think that would probably remain the same. I mean, as we get to the 15 billion people, we're going to have just that much more electricity consumption also. So I think that'll remain a small fraction. I'm curious if anybody happens to know that answer, how much CO2 people produce in the course of a day. I've never looked at that. Okay, so you have a question?
I was just curious about the absence of nuclear energy in your presentation.
Ah, right. Yep. I mean, nuclear energy, of course, is fossil free. And but my sense is that it's just expensive. And these systems are coming out pretty inexpensive. They're below 10 cents per kilowatt hour and heading down toward 5 cents per kilowatt hour. And I just don't think that nuclear can match that price.
Yeah, I'm paying a little bit of attention to that, and I think you're absolutely correct when you think about these massive nuclear facilities that we installed back in the '70s. There's a lot of technology development work going on with this so-called small portable nuclear units. I don't know what those cost profiles look like, but my guess is they're significantly lower. Maybe, or could be a part of a solution.
Do you have a comment on that?
They're more stop-start friendly than a gas topping plant. My sense is a gas topping plant would have to run all the time at its lowest rate.
No,
As opposed to just cranking it up for 2 days and then shutting it
No,
down.
you actually can. That's the interesting thing about the peakers, that, the capital cost is so low.
I think they would have to be online. Everything would have to be at some temperature to operate.
Well,
I could be mistaken, but most chemical processes need to be at some state of operation in order to be cycled up and down.
okay. Lee,
no individual nuclear plant can be turned on and off to help the reliability problem. There's this xenon poisoning problem. They have to, once you turn them off, they have to be off for a few days. The reason those smaller plants get more robust is because you have more of them. But any individual plant, once it's turned off, it has to stay off for a few days.
I didn't know that. Thank you.
My question has to do with the battery storage costs and what exactly, is this after capital, after you make the plant, the storage batteries, and then what is that cost?
well, it's an optimistic, let's say, okay, so we're looking at that picture there. So it's really the cost to build those storage units in the upper right picture. And so it involves the cells, but then it also involves interconnects between the cells, and it involves various kinds of transformers and things like that. And so, I think the 200 is actually kind of an optimistic estimate at that point.
But that's the capital cost, but what about the maintenance cost? I assume that's what you're talking about.
Yeah, no, so
All that maintenance.
well, the maintenance, I did the economics here was very simple. I just assumed that for every technology, there was a capital cost, and it would expire after 20 years, and we'd have to make a new one. So that the maintenance would go into that. So it's like basically a depreciation.
Okay.
Do you have any thoughts about how to move from the science world of optimization studies into the political and public policy world of actually implementing it? It's one thing to have the perfect system designed, but it doesn't mean anything ever happens.
Right. That's a really good question. And to be honest, that's not my strong point. But I'm frustrated kind of sitting here designing optimal systems, and I know that they won't necessarily get reached. Now theoretically, economics gives us a cost optimizing system, but that's always decisions that are kind of based on current conditions, and are they going to reflect future conditions correctly? That's not clear to me.
I have a question. What about the idea of Bill Nye talked about using big heavy weights to store energy? Like we used to have those things for gas, those big gas tanks go up and down. What about that?
Yes. There's been a project where they simply lifted heavy concrete blocks from the ground, and they lifted them maybe the height of a football field. But again, the cost there, they were aiming to get the cost at around $200 per kilowatt hour when I saw that. So that was the aim. And these are pretty large things. It turns out the energy density is not all that high. So compared to those, I think future battery technologies are going to be significantly more practical than those.
What about burning the hydrogen directly? Is what storing it? What's the idea of just generating the excess electricity and just burning it, putting it in our gas lines? What about that option? I know you hinted at that a little bit.
Well, let's see. You mean using that to heat?
Store, yeah, and using, yeah, you burn the, you have excess solar stored and make electrolyze the water, and then use the gas and then burn the hydrogen directly. What about doing that?
Let's see, you could burn that's true, but then your efficiency is really getting low.
Oh, okay.
But then you have to hydrolyze the hydrogen and then burn it. And I think maybe it's roughly the same efficiency issues as with the fuel cells. Yes.
Can you speak to growth and impact of distributed energy systems?
Now, by distributed energy systems, you mean that like in a community?
Less reliance on the national grid.
Yes, I think there you now, I have solar panels in my house, and I benefit hugely from being connected to the grid, because whatever extra power I generate, I can send back to the grid and then get it back and so on. And so, but in distributed energy systems, you're trying to be less reliant on the grid, and so then you have to deal with larger fluctuations. No way of getting around that, and so you have to have some way of dealing with that. So then the storage and the backup, it becomes a bigger part of it. So certainly it's going to be more expensive, but it might be worth it for the independence.
Let me ask this question. You showed the electrical grids in the United States. 20 or 30 years ago, Con Ed went out. And the electrical activity went off in the eastern part of the United States. Would the government ever have an economist look at that to see how much cost there was lost by the electrical grid going out and being able to transfer that energy to other places in the country, so you wouldn't lose that, you wouldn't lose the economic impact of a whole grid going out?
So, I mean, I don't know if they have looked at that, but, certainly, I mean, I think as an argument for an improved electrical grid, you can just look at the lower cost of electricity also. It's like a 20% drop in the cost of electricity with a fully connected grid across the United States.
Back to what you were talking about electrolysis, looked like you were talking about using energy from solar cells to do it. Whereas for a long time, there's been interest in trying to develop some kind of catalyst to directly translate sunlight, use sunlight directly in some kind of catalytic process, generate hydrogen. Right. In theory, that could be super efficient way, right? That would be
direct photochemical conversion. Yes. Yep. Again, somehow that's not what seems to bubble up when I see what's hot at DOE.
You'd have to be arguing that that's better than photosynthesis.
Well, better. If it was good as, that would be plenty limited to generate hydrogen at that rate.
How much R&D money is going in to the study of renewable energy?
Well, let's see. I mean, I get these notices from DOE that occasionally we've awarded another $100 million and another $100 million.
And then the other, who's doing that?
Sorry?
Who is doing this? Where's the money coming from? What?
It's coming from the Department of Energy. They have been getting serious about funding renewable energy research. And then it's going either to universities or into companies. Okay, well, I think, let me take other questions in private, just so people that want to get going can get going, but I'm happy to stick around here and talk a little bit longer. So thank you all very much.
Like, does that make a significant difference if you have one? Why go to the all of these electric cars that aren't moving, just sitting there being backed up storage for the grid?
But you don't need to go through that because it's you somehow have to make some assumption about their availability. Like when are they available and when do people need to use that energy of the cars? I don't know. haven't put that into this.
I have no idea, but my cars aren't moving most of the time.
Correct.
Yes.
Hello.
You can't, yeah, the new car don't work.
As they
Not the
migrate
colors
to
are-
that's a large factor.
Actually, the Chernobyl accident was because they dropped it down.
For individual homes.
Right, and even just at that level for your own house, you sort of have this like built-in battery.
You bring a reactor down or shove it,
Connectivity issues though between the vehicle.
let a certain thing decay, and then you can start again.
In order to have energy that's sitting in that battery, like run your lights.
Yeah. And I'm not sure.
Prices might be much lower.
Either, it seemed like factory with big work trucks would have like a big battery in them.
You're not still.
It's like, oh, you can go to your job site and run all your tools and everything off your truck.
Yeah.
And it's a little different than running your house.
Leveling.
Sort of like that idea though.
I think it should be a part of it.
This is all really interesting.
The things like,
Yeah.
with something.
Figure it out soon.
Times cheaper.
I'm thinking.
Yeah, well,
We never solved that problem. Still.
we haven't, but
Is it really
I
scale?
don't think that's
I understand that in some way to be.
Either at a national lab or to be converted into something useful. So my picture of it now is being student. Somebody at the university gets a research.
maybe have been the right thing to do.
They
Because
some bright idea, and then DOE has another,
decaying,
they have another.
stuff switching process a lot easier.
And actually.
Makes sense actually to have local,
So, all those pieces are in place. I think they're way too small.
all designed,
You're probably
store all of their waste on site for their entire running time.
on that
On
grade.
site. Yeah, and then, or maybe another 100 years, and then you can decide what to do with it. Right, when it's on it.
But I was thinking though, transporting, hydrogen is
And Geo.
significant transmission.
For 10 years, called the Joint Center for Energy Storage Research, which was a big grant. It was about $200 million grant, which funded a bunch of university, mainly a bunch of university schools. But they push things along.
That's no different than current gas.
So, I think DOE has a pretty good approach to this.
It's
now.
actually less energy dense.
When I had,
Oh, yes.
I wanted to do research on solar cells. No, we don't do research in energy. It was strange. But no, I feel like they have their. heads on straight now.
Why make hydrogen?
Okay.
I'm just gonna.
Well,
Storing energy in.
There was a commercial scale plant recently.
Just because
This
this
was
is
an
very common around. Brought up, very common. You remember
Natural
that?
gas.
That you, every house that had a little generator.
And the paper process.
Except with, to be,
And you can see it
to be green, you need that gas.
But where does?
I'm
this
not,
thing
I'm
end up?
a
Can you do that?
advocate of this. And
Same thing you showed.
Yeah.
But
I think
does it
that's, I
actually-
like.
Does it sit there at gas or does it?
Yeah.
It wasn't clear. They just
Okay.
said they were.
I didn't think about, they have a lower.
Registration.
Yes.
Okay,
So
Yeah.
basically zero emission.
right, yeah, I mean,
But it
you just hope
wasn't
it's,
clear.
you just hope it's really sequestered, like sequestered
So,
for
example.
100,000 years instead of
I
500.
thought it was interesting. They're gonna generate hydrogen to sell hydrogen.
Almost
Oh,
all hydrogen.
okay.
It's a commercial hydrogen
Why?
plant.
So that when you
It converts methane to hydrogen.
oxygen,
Dealing
the,
with
you are below.
Okay.
So usually.
Canadian company, Enbridge.
Yeah. Most.
Provides them not tied to these. That the actual
Scales
gas.
and all
I
this
can't remember
stuff.
the name of this. Company that's.
Yeah, well, that you're not even talking about.
I thought it was in commercial scale.
Yeah,
This is not a-
No, we couldn't.
Not a startup. This is,
Anyway, thanks.
Okay,
commercial scale.
that's very encouraging. All right,
Enjoy it. Thank you.
You were starting to talk about the politics of implementing all this stuff. You guys came up with. As I started talking to this guy, Leland, up there, and he said, do you know the concentration of the CO2 in the atmosphere? I said, no, not offhand. and included some number of 0.0014 or.
420 parts per million.
Yeah, well, he said that can't possibly have any effect, and these guys are all wackos. Pointing to down here. So, I mean, I said, well, it has the number means nothing, it's the effect of the number.
Right.
You know, the evidence is, you know, and he was, but this is,
Yeah, I mean,
this is what you're facing,
yeah.
I mean, you know what I mean?
Yeah, well, that's true, you know, but some of it is how do you describe it? You could describe it as so many parts per million, or you could describe it as a trillion tons.
Right.
And if you think of it as a trillion tons, maybe it seems a little bigger, even though of course it's the same number.
But he's.
It doesn't take
one
much,
number.
it doesn't take much ozone to totally change the absorption.
Oh, ozone especially, yeah, I mean.
So, yeah, so I'm just making it different.
Yeah, I see. what
We
you
don't
mean.
need much ozone to protect us.
Right.
We don't, and similarly, this amount of CO2 can totally change the atmosphere. So
Right.
the fraction is not.
That process doesn't go into their thinking, you know what I mean? It's, how do you get by that? So maybe next time you should say, this number is small, but it has this, some way to, you know,
Yes.
get through to
You're
these
right.
people,
You're right.
you know what I mean?
Yeah, anything with a bunch of zeros in front of it just doesn't.
Yeah, I
seem
guess,
like
well, that
anything
could be,
important.
these guys are crazy, you know, they're putting on. Anyway, enjoyed it.
Okay, thanks for coming.
If you looked at this plan from Oak Ridge, I think it's called Mars. It's a network. It's a redesigned power grid. Mostly for the, it leaves out the East Coast and the West Coast, but certainly breaks some of those boundaries.
Mhm.
And it has integrated AC and DC components.
Okay,
And
so
but I don't know much
and you
detail.
anything about like how many gigawatts and stuff like that?
I don't know. I just know the acronym Mars. So if you search
Good.
Mars in Oak Ridge, it's a plan. I mean, it's a national lab generated plan for an improved grid that presumably has built in some of the optimization strategies that you thought about.
Okay,
And it's, you know, it's DOE. It's not a national plan, but it's, I mean, it is an effort that has been put out by the Department of Energy, say we could do this.
Yeah.
But I don't know details, and would like to know.
I wish I did too, yeah. In fact, that's what, before this talk, I wanted to learn more about the grid, but never could find anybody good to talk to tell me about it.
Yeah, so nuclear can play no role in your optimization.
That's my
because
assumption.
it can't go on and off, but it could. So if you have if you decide you don't need a base load, then you don't need a base load, but it's firmly in the base load area. So,
Okay, but what is that in terms of cents per kilowatt hour?
The old ones that we have now, you know, they're dominated by the on-site construction costs. And that's been a killer. And the new ones that someone brought up, talking about it, called small modular reactors. They're built in a factory, their costs, construction costs should be. But, you know, you still have a lot of problems. So, you know, whether, you know, nuclear is very complicated because, you know, you'd like to say, you know, you have this picture and you want to, you know, you have a mindset, and I'm not saying it's a wrong mindset, but it's a particular mindset of how you'd like to see the world. And it's very wrong in a certain sense. So, for example, why is you know, so Russia is building nuclear power plants and exporting them. South Korea is, many places